So let's start the first lecture. Okay, the first 3 lectures, we did a little bit of check cohomology. And so the idea is that it was purely topological, in the sense that if we take these topological spaces, if we take these topological spaces, then using check cohomology, we associated these spaces. This sometimes the point comma z. These are actually z modules or abelian groups, and so the homology I didn't focus too much, and since we don't want to lose too much time with the basics of algebraic topology, maybe just if we want to follow the things with homology, it would be safer to use, instead of z, the coefficients, rational coefficients. And let me just mention that the homology x, y. So if we take the sheaf of constants in the field of rational numbers, so this will be just the cohomology, the check cohomology that we constructed. Oops. And taking dual. This means that all linear maps from this will be a Q vector space, all linear maps from this Q vector space to Q itself. And so even so that during the course in my book, you will see that there will be Z here. If you have not done a course in topology, in algebraic topology, maybe it's safer for you to replace Q, because if you put Z here, there will be the issue of torsions and some extra information from algebraic topology it is needed. Okay, this is so the idea is that along the way, a bunch of axioms. So this a bunch of properties. So the idea is that let's say satisfy a bunch of properties. And one idea of the course is that just a moment. Okay. During the course, we will see these properties, and without proof, of course. But I think it is. At least my impression is that I know a lot of physicists working using these homologies, cohomologies, and without caring about the proof of all these properties of the homology or cohomology. And that then the idea is that to use correctly these properties and axioms of cohomology. And maybe another one that it would be, I put it as exercise 1, that this would be also very important, that H, let's say N, unit ball with boundary in, and then S, its boundary, Z, this is isomorphic to Z. I think this, which will at the end, this will be implied that H, N, S, N, Z, this is Z. And last time I told in the Bottu's book, there are cases which he treats this one by taking a covering, a good covering, and so on. So I think if you have never seen cohomology theories, maybe it will be good that you do at least this exercise, and then along the way you'll learn the properties. Okay, so so let's stop with the topology here and return back to algebraic geometry. I will use a complex version of algebraic geometry, in the sense that not too much focuses on algebra, but more in geometry. Okay, what so our, as I said, our basic examples are projective varieties. As I said, this is given by homogeneous polynomials, and I need this to say that when x is smooth. Let's just very fast remind this concept. And actually, in my way, I will need also maybe something more general. Let's try to make this definition. If I have two varieties, two subvarieties, and then I want to say that when x intersects y transversely. So for our main purpose, we need to define these concepts, and then of course x, y is smooth. I need to define these two concepts. Okay, so let's try to do this one. First of all, I will this is a let's say intersecting transversally is actually at any point. So it's a local. When you just take the topological intersection at x and y. In the intersection of x and y, we want to say what it means intersecting transversally. Of course, smoothness also, we have to divide the point. X is smooth. It's smoothness at points. So we have to focus. We have to consider local aspects of projective varieties. And so for this, let's just forget the projective. We will take charts. So for example, this chart, let's say x. Remember our notation: x0, x1, xn, such that xi is not equal to 0. And actually, this is how let's say, let's not definition. Let's say this is a kind of isomorphism. So the isomorphism here for up to here, how it is given? It is given by just x0, xi, and then xi minus 1, xi, and then jumping xi plus 1, xi, xn, xi. So we will take these charts, and then we will work our charts. So let's say so when we look in this way, then x and y. Let's say maybe it is better that I put x1 and x2, because I will need this y as a subvariety later. x1, x2. And then let's put this one x1 and x2. x1, x2. Okay. And so in this affine charts, the variety xi is given by polynomial equations. So x1, 2. Let's call this one ui. In ui, are given by zero set of polynomials, not homogeneous. And okay, so let's by polynomials, let's for simplicity, let's say if this is let's say it is let's say Cn, I will use the coordinate x1. It's not compatible with this the coordinate notation of the projective space, but since I am fixing the chart, I will use just x1 until xn as the coordinate of Cn. Okay, so so what is the notion of x1 intersect x2 transversally? So let's go to part of my own book. Let me explain a little bit from what is written there. Okay. Okay, let me see. Okay, so let's go to this book. Okay, and so today's topic is mainly about this chapter 5, but let me go to the exercise. Actually, this is the second exercise that it would be nice you do it. In this way, you get a little bit familiar with basics of algebraic geometry. Okay, where it is. Okay, so let's the exercise. Exercise 5.1. And actually, most of the content of this chapter is taken from an article of Lamotke. It is one of the really beautiful articles that I have read in my life. It's about reconstructing Lefschetz's original proof of his theorems. Okay, but anyway, let's so if you have let U be an affine variety given by the zero set of finitely many polynomials, and let's just take a point P. So the smoothness that the definition of smoothness that I'm using, it is basically from differential geometric notion. And if you do course in classical algebraic geometry, then you will see a more algebraic version also. So a point P in this U. So U is our X in the affine chart Cn that we have chosen. So okay, so a point is smooth if we can find these polynomials, which actually these polynomials they are zero on the variety U. And when we form this map, and so let me read. It is smooth if there is a polynomial map where P1 are our polynomials and S is less than n, such that in the Zariski open neighborhood P in Cn, the differential of f has maximum rank S, and U is the inverse image of 0 by the map f. So something that in analysis we learn, it's this implicit function theorem. If we have a map from Cn to Cs such that its differential has maximum rank, then its level surface or level manifold, it's smooth. And the definition that I have chosen is this one. And so the smoothness, let's just use this one. And okay, then we now we can also talk about the codimension, and that S is the codimension, n minus S is the dimension of U near P. Okay. Maybe for okay. So I need also the hyperplane section. This is let's say if I have another variety given by a linear equation. In this case, it is let's say a polynomial of degree 1, and I put it 0. It's called the hyperplane. And I say that it intersects U transversely at P, if of course the hyperplane crosses that point. And again, the differential of the map, this F, together with G, again has maximal rank. This means that if I add G to the list of P1, P2, PS, the differential its rank drops 1, so it will become S minus 1. And okay, so this is in general what I wanted to say. Also that the concept of maybe let's return back to the handwritten. Okay, just a moment. Okay, so what I wanted to say that let's say since I use x and x1 and x2 for projecting, well, let's now use u1. Actually, no, one u2. Affine varieties p u1 u2. So u1, let's say, intersect transversally. This is the notion of a transversal intersection. U2 at P. So what would be the definition? Remember that for U1 we choose let's F. Let's say F P1, P2 until PS from Cn C. Let's say CS. Let's say defining, let's say F minus 1, 0 near P gives U1. And maybe let's take the same for, let's say, for U2. So G, let's use P tilde. F tilde, P1 tilde, blah, 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 PS tilde, and then Cn, and then there will be maybe different S, maybe due to different codimensions, so that it will be S tilde, let's say, Cn until CS tilde, and the same tilde, F tilde minus 1, 0 near P gives you 2. And so what would be the natural definition of U1 intersect U2? That at the end, let's say, if so this will be if you put F tilde let's say Cn to CS plus S, then as maximum rank. Let's intersect. Then what would be at maximal has. Let's write it. Let's write it in a different way. It's actually in this in all this case we can put is. That's it. The differential of this map is surjective, and the differential of this map, let's say at P. So it will be S plus S tilde times n matrix formed by the derivations of f and f tilde. So, and then we have this this notion. So, well, for the moment, my notions of smoothness and transversality will be more differential geometric concepts, but later maybe we go also more purely algebraic versions. Okay, let me any question? Okay, so now let's go. Today I want to give to present the main theorem of the topology of algebraic varieties. So let's just try to read the parts of my book. Okay, so let's okay, so I want to talk about this main theorem, which let me say many theorems of Lefschetz is based on this one, and I had to a little bit combine this many main theorems about topology of singularities, classical theorems of Lefschetz to get to formulate this theorem. Anyway, so let's again take a X smooth project for a dimension n. It's inside Pn, and so I will need two transversal hyperplane sections of X. So remember that hyperplane section means that I take a linear equation in Pn, and this linear equation must intersect the Pn transversally in the sense that I told. By the way, it's a very easy. Well, it's a kind of consequence of the main theorems that if this hyperplane section intersect y and z, let's say if you take two hyperplanes, h1 and h2. Let me say right here. So maybe I have to write here. So I take h1. This is a hyperplane in Pn, and then its intersection with x. I call it let's say y. And then to other hyperplane section h2. Let's say x. I have ordered the touch screen monitor. I hope that it will make my writing better. But anyway, let's. Okay. Anyway, I take two hyperplane h1 and h2, then their intersection with x, y, and z. And because of the transversality, it is easy to see that y and z are smooth. And something actually extra that we have to assume that this y and z itself, they intersect each other transversely. This will be also important. And this assumption also will be is important, so that will be extreme. So we will have x, we will have z, we will have y inside it, and then we will have x still, which is the intersection of z and y. Everything is smooth. There is no strange singularity popping up. Maybe another picture, better picture if you want. This one, actually, here I have called it h and h tilde. So as I said, hyperplanes are just the copies of Pn minus 1 inside Pn. And just to keep our intuition going on. Okay, so I need this situation. And okay, one maybe something actually that during this our Hodge theory study, we will not I will not need it. Let me say what. So maybe we do not assume that Y and Z are hyperplane section associated to the same embedding. Maybe this is let me explain this one, and this is actually the small contribution that I had to do in this book. As I said, that our main theory in this lecture is a kind of historical. But anyway, I had to make this small modification in order to be able to apply it in many different situations. For this reason, maybe let's recall the Veronese embedding. I think if you have not done algebraic geometry, let's do a little bit also algebraic geometry here. So maybe I stop here and let's talk about a little bit Veronese embedding. And okay, so okay. Let's just a moment. Veronese embedding. And let's say if you have Pn, as I said, you put let's say x0, let's say the coordinate x0, x1, xn here, the projective coordinates, and then you define another map to something bigger, let's say S. And what is this map? In each coordinate you put let's say x, maybe I write beta, blah, 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 blah. So you put here all homogeneous monomials of degree d in, so it is let's say it depends on some degree d. So we have fixed a natural number n of degree d in x0, x1, xn. So this means that we form all these monomials, and so that's how many monomials we have. Let's say if I remember correctly, the number of monomials of degree d in n plus 1 variable is n minus 1 d. Let me check this one. If d equal to 1, it must be n plus 1. So actually it must be n, actually this one, yeah. So that actually this S that you see here is this. So the number of monomials in of degree d in n plus 1 variable is this one. You define this projective variety, and then the map is given just by all the monomials. And it is well, it is it's known that it is it's an embedding, so it gives you Pn as a subvariety of this Ps. So you see that the dimension of the projective spaces increases. But what is it useful for? You see that if I have a hyperplane in PS. If I have a hyperplane, this means that it is given by let's say let's say the coordinates here denoted by y0, ys. If I have a hyperplane here, and if I make the pullback of this one to a hyperplane to PS, then it will turn into a hypersurface. Hypersurface of degree d. This means that hypersurface given by a polynomial, homogeneous polynomial of degree d. So it's a kind of so the main idea is that even so that we are talking about hyperplane sections, but actually by using a Veronese embedding, we can transform it into hypersurface sections and so on. So yeah. Okay, so let's. Actually, just a moment. This S is -1 because of the projectivization. So the number of monomials, this one, and then because of the projectivization, we have to the dimension of this projective space is this. Okay. Okay. So let's have this one also. So let's
Hossein.
Back to the book again.
Hossein.
Oh, Felipe?
Yeah. Which properties of the hypersurface can we obtain looking at the hyperplane?
Just a moment.
Oh,
I think there is some problem in my.
Is it okay? Can you listen?
Felipe, você estava escutando?
Sim.
Teve algum problema porque parece que minha altavoz não estava funcionando.
Oh, tá funcionando. Tô te ouvindo.
Tá. Então.
Okay, so which properties of the hypersurface can we obtain looking at the hyperplane? Like, how can we know if the hypersurface will be singular or not by just looking at the hyperplane?
No, this is the
geometrically.
Let me if I understand the question. So we have well, as I said, I want to say that hyperplane section is the same as hypersurface section, but at the end using the Veronese. So you want
yes. Sorry, you can continue.
And what I am saying, if in the middle of I said, okay, let's just take hypersurface intersected. After Veronese embedding, this is the hyperplane section.
Yes, okay, but well, no, I understand that, but my question was more general in the sense of what are the geometric properties of this identification? You know, like how this hyperplane we get in the bigger projective space relates to the original hypersurface and vice versa. Like, but I mean, it's not really important for this.
Okay.
I think.
No, maybe I think you have to consider that at the end. Let's make a picture.
Yeah. Oh, okay.
That's a PN. This has let's say it's a P. This PS. And let's say so. The point that this guy has image. This is a variety here. Okay. So this is the image of this V map. And I mean, hyperplanes here are very simple, but hypersurfaces here, they might have singularities and so on. So the thing is that if you want to translate it from one side to another one, here you have to consider how the hyperplane intersects this variety, and then this will be translated to something. So as I said, hyperplane in themselves, they are always smooth, and all these concepts like singularity and so on has to do with how this smooth thing intersect the image of the Veronese embedding.
Okay, now I understand what you mean.
So it's not just trying to translate from something about hyperplane to be translated into something about hypersurfaces. Something about hyperplanes, how they intersect the image of Veronese embedding, it will translate to some property of the hypersurface itself.
Okay. Yeah. Now I understand. Thank you.
Okay. I think for a few seconds my sound device was not working. Anyway. Okay, so let's go to let's see what's done. Okay, so let's go to to present the main theorem. Why I needed this this Veronese embedding? One observation is that when we use Veronese embedding, then a Pn itself can be considered as, let's say, some subvariety of another projective variety, and we can talk about, let's say, hyperplane sections of Pn, because when you look Pn inside this PS, again, we can take hyperplanes here and intersect. So this is, let's say, this is something isomorphic to Pn. And let's go to the book. Okay. Maybe this observation that I here, we don't assume that y and z are hyperplane section attached to the same embedding x. Maybe in the book I have written again a little bit more general. So let me see. Let me one situation of this. Maybe I can explain it. So there is this concept, this notion of divisor and so on. But actually, I don't need this thing that is written. This is for maybe some of the people who knows more algebraic geometry. Maybe this class of this. Maybe I a little bit explain about this one, and okay, maybe I will. Let's go. Okay, let's do in this way. So for the moment, just assume that y and z are the same are associated to the same embedding. So they are hyperplane in the same embedding. And then after announcing the main theorem, then I will return back to this small generalization. So okay, so just remember our picture: x, z, y, and x x dot, which is in the intersection. So the main theorem that for a few lectures we will be around this theorem and its proof is this one. Okay, so this is the kind of the cohomology that we will try to prove it. So I don't know how you make you want to make the intuition of this one. You remember that first of all, the idea is that we want to remove z from our x. So we have removed z from x, and of course, and we want to consider cohomologies with the boundary in y. By the way, since I have done check cohomology and not homology, maybe just you put this q that you see here, just put it upstairs, the same theorem, and then still it is valid. So let's just consider that if it's q, if you want, you put q here. And okay, so we want to consider the cohomology of x, the pair x and y, but we want to remove z. From x we remove z, and when we remove from y the z, we have to remove the intersection of y and z. So this is the x prime. So it turns out that after all the transversality assumption that we have made, this has no cohomology. This has no cohomology in where is the mouse? I think something bad is happening to my computer. Okay, just a moment. Okay. Okay. It's very strange. Okay, the pointer. Okay. I think I have. Okay, so you see that just in the dimension of the variety, we have a free Z module. So this is free. There is no torsion, and apart from this one, all the cohomologies are 0. So I hope that during the proof of this theorem that we are going to do, you will learn also the basics of algebraic topology and all the properties of homology and cohomology. All the axioms and all the theorems, basically, they will pop up in the proof of this theorem. So in some sense, the proof of this theorem will be a kind of a crash course in algebraic topology. And okay, so let me say, as I said, for the moment, if you want to put it just a cohomology version, maybe. Okay, maybe I return back to this assumption that not necessarily x and y comes from the same hyperplane sections. So let me a little bit explain this one, because I want to make I stop sharing. Okay. Maybe let me explain one instance of this theorem, which takes us to the area of singularity theory. Is okay. So let's P is Pn. So actually, I want to apply this to this theorem to x Pn itself. As I said, if you embed the x in another projective variety by Veronese embedding, you can talk about let's say a hyperplane section and so on. And Pn minus 1. So let's take this one, and you can see that, for example, I just want to take this. Let's say x0 equal to 0. So let's say let's write in this. Let's write in this way also x Pn such that let's actually x0 equal to 0. Okay. Just a minute. My sound device is failing. Okay. 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 So one hyper. Well, if you do a Veronese embedding, it is you can. Let me say. Actually, this is already a hyperplane section, because x0 equal to 0 is just the hyperplane, and then the intersection with Pn is the whole space. And okay, so I want to take this y a hypersurface in Pn. And by the way, I didn't mention all this x, y, and z. They transfer, they intersect each other, transfer. They are all smooth. We are all in this smooth, and everybody intersecting the other. Everybody is transversely. We are in this context. Okay. So z, y, x, everything is consummed, and then hypersurface in Pn. So this is smooth. And let me. What else? So it will be given by, let's say, x in Pn such that fx equal to 0. So f homogeneous polynomial of degree degree D. Okay. So as you see, slowly I will start just writing f equal to 0. So this is the abbreviation of my notation. So okay, so let me, and you see that in this context, y and z, they do not correspond to hyperplane in the same embedding. Remember, z is already a hyperplane, so it is, we don't need to use Veronese embedding. But in order to make y focuses, okay, in order to make in order to make y a hyperplane section, remember that we have to use Veronese embedding of degree D. By the way, well, okay, y is smooth, z is smooth, and then let me add to exercise 5 point. I add a few other things. So first of all, y is smooth. Then just convince yourself this is the same as to say that the Jacobian ideal 0 of fx0 fxn n, it must be just the origin. So the 0 set of the partial derivatives of f must be just the origin. And okay, this is one additional to the exercise 5.1. Okay, so I want to a little bit discuss this y intersect z transversally. And in order to discuss this one, I will choose, let's say, this Cn, Pn. So this given by x0 equal to 1. So in some sense, what I have this Cn is just my Pn minus this Pn minus 1 that I had. This is also, I'll call it Z. So maybe let's make the picture. So I have I will my picture of something like this. I have this Pn, and I have Cn as a fine chart, and at the infinity I have a Pn minus 1. Okay, which I called it also Z. So, and of course, let's. And of course, I have this Z, this Y variety. Okay. So let's return back to the Z notation. I call this one Z, and I call this one X prime. So what I am going to say that the theorem, the main theorem, is also valid in this context, even so that Y and Z they do not correspond to the same same embedding, and say they do their hyperplanes do not lie in the same projective space. Okay, so, and maybe let's a little bit write this. What is this y intersect maybe another extension of let's say exercise 5.1, and actually exercise 2 of the course. Slowly I will exercise 2 of the course. So why before this one I have to remember, let's say let's call this one, let's call f let's say x0 equal to 1, and then x1 until xn. So my variety y in the affine chart Cn is given by this small f equal to 0. So let's say y intersects z transversally. Let me just Actually, it is if and only if. So even so that we formulated in a more geometric way our transversality and smoothness. So the idea, one good idea, which happens always, that the things are translated into more algebraic statement. So in this case, it says that if I write homogeneous decomposition, fd minus 1 plus fd. So this means that this fd is fi homogeneous of degree I. So if I write the homogeneous decomposition of my f, then this fd, well, I will call this fdg. Then let's say 0 of now this g x1 g x n. This is also 0. So the 0 variety of the last homogeneous piece of our f must have isolated singularity at the origin. So this is so this concept that you see both for f and for g. In the singularity theory, the people use this, that this f equal to 0, capital F equals 0, or this g equal to 0 has isolated singularity at the origin. And partially our proof of the main theorem will have to do with a lot of arguments in singularity theory. So let's return back to the so you see that in this context we have a complete control of our transversality hypothesis. Basically, f will be smooth. We have to have this one, and then must have this one. And if you want really example, let's say just take our main example in the course will be the Fermat. We have this notation x n to the d. This is the example that we will take it. And so if you take in this case, f will be 1 plus x1 to the d, blah, 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 xn to the d. And what else? What else? Then what is the last homogeneous piece of this f, just cutting a 1. This will be x1 to the d plus xn to the d. And of course, this and this, they satisfies these two conditions that we have. And so in particular, our theorem is valid in this case. And let's write our theorem in this case a little bit differently. So maybe I write it this one. Okay, so HQ, as I said, so x minus z. What is x minus z? X was the whole projective space Pn, and z was the infinity. So x minus p is just the Cn, the affine chart. Yeah. And then the boundary was y minus x spread. The y is the hypersurface, and we are cutting the z. So this means that we have to cut x line. And but what it means, this means that let's if I call, let's say, this u, so u will be f equal to 0 inside Cn. So the affine part of my hypersurface. So the basic our main theorem is that the cohomology of Cn with boundary in u, let's say in z coefficients, it will be 0 if q not equal to n. And you see that here in this case, our ambient specific dimension capital N, and it is free. Let's say it will be some z to the mu 1 when it's q equal to n. So you see that in this case, what it says, the cohomology of Cn with boundaries in a smooth hypersurface, a smooth affine hypersurface, which intersect the infinity transversely. This cohomology has 0 for q not equal to n, and it is free for q equal to n. And some ideas comes from singularity theory. This will be related to Milnor number. A lot of things that we will use from singularity theory, and my impression is that the classical people in Hodge theory, they do not appreciate it too much. And but we will use these ideas from singularity theory. Maybe the next lecture will be focused on the proof of this theorem, which is basically chapter, let's say, chapter 6, which has to do with Picard Lefschetz theory. I will try to find a minimum way to present the proof, but as you see, the chapter has more pages, a lot of data, and so on. Okay, maybe something before finishing. I say about this, maybe just a kind of intuition. And let's make a three-dimensional intuition. Just imagine that we have a, let's say in Cn, this is our u, which will be with which. Okay, and the point is that there will be we will find the real ball of dimension n with its boundary. We will see that we will find fi, I don't know, alpha I equal to 1, 2, 3 until mu. So what I want to say, maybe I am talking a little bit about the generators of this guy when q equal to n. And so during the proof, we will construct the mu maps from the n-dimensional ball and its boundary is n-1 to this ambient space. So the boundary will go to here, so the s n-1, and the ball will itself go to the whole space Bn, and we will see that these we will call these sphere-like. Actually, they will be embedding, C infinity embedding. You see that now here we are in algebraic geometric concept, but for the homology and cohomology with Z coefficient, we have to do topology, and these maps will be C infinity maps. And let's say we will construct mu of these maps. As I said, this will be C infinity embeddings. With this will be called Lefschetz vanishing cycles. Lefschetz vanishing cycle, and this will be called Lefschetz thimble. Lefschetz thimble, And in some way, the union of all these mu will give us the generators of the of the cohomology that we want. So if you want a little bit read before the next lecture, chapter 6 about Picard-Lefschetz, we have a look at that. And we will need a Thom Leray-Gysin isomorphism, and then I will also present it in the next lecture. Okay, I think for today I'm done. Maybe let me see if well, any question. Maybe I stop recording and then just a moment.